If, by the way, I'm David. I'm a, my title is Chief Software Architect. Let's look at FLAC2D's groundwater logic, the fluid logic. Called Darcy flow. It's not a full CFD code in any way. It's just straight up Darcy flow. We can do isotropic or anisotropic permeability, basically whether you give a scalar or a tensor. And we do have both one-way and two-way coupling between the mechanical and the fluid logic. And I'll talk more about details about that later. By default, we do unsaturated flow. So pores can desaturate and go to zero, and then there's an automatic phreatic surface calculation. I want to be very clear that a lot of what I'm saying is in the current version of FLAC2D. As it happens, one of the reasons I'm teaching this course is because I just spent the last several weeks completely updating the fluid mechanical interaction in the code. Those changes did not make release. They'll probably come out a few weeks after release. They are designed to make a lot of this much easier to use and to move from simple to more complicated gradually. I'm going to mention some of those changes as we go along, so you're not surprised by them when they come out. But we're going to have to teach the current version of the code right now. Okay. So by default, we get the full phreatic surface calculation. So if the pore pressures try to go negative, they won't. They'll just desaturate pores instead, and you'll create a phreatic surface. All our constitutive models use effective stress. So when we're talking about, and this is a point of some confusion, I want to be very clear. When we're talking about stresses in zones are by default always total stresses. So they're mechanical stresses plus pore stresses, pore pressures added together, okay? The effective stress is the total stress minus the pore pressure. So you can think of that as the cartoon in my head is that you've got like a sponge or a matrix of material filled with water, and the water is carrying some of the pressure. It can't carry any shear because water doesn't have any shear resistance. So it's carrying some of the pressure, and that reduces the pressure in the material, but it doesn't reduce the shear, and that can bring it closer to the failure surface, right? Because normally, more cooling material, for example, the shear strength is related to the normal stress. If it's got less normal stress, it's got less shear strength. So by taking up some of that shear, it reduces, it gets it closer to the failure surface. It's more likely to fail in shear. And that's kind of a fundamental of effective stress theory. But we'll talk more about that later. The point is the FLAC2D zones are total stress. If you want to look at effective stress and subtract the pressure, the pore pressure out of it, there's a separate plot for that. You can find it on the list. But the constitutive model always sees effective stress. It's the only thing the constitutive model ever sees. We take that pressure out, pass it to the constitutive model, and add it back in when we're done. Okay. And we do two-way coupling. So we alter the effective stress for the constitutive model. We alter the stress the constitutive model sees. But we also, when the mechanical logic generates volume changes, it will automatically generate pore pressure in the fluid. That is also the default setting in the current version of the code. In the updated version, those will not be the defaults. You'll have to turn them on to make it more complicated. But right now, we start off with kind of everything present. All right. So for those of you who've done some theory, a lot of time people always work in terms of head, which is kind of like the height of the water sort of table. FLAC2D does not work in head. FLAC2D works in pressure. So you can move from one to the other, and thanks to Joe, that you can now plot head in addition to plotting pore pressures. But know that really, fundamentally, FLAC2D works in terms of pore pressures at the nodes, not the head. Okay. Also, another little side note: compressive stresses are negative, so negative values are compressive. That's not true with pore pressures. Positive pore pressures are compressive. A little bit inconsistent, but that's just like the standard we use, okay? So positive pore pressure is compressive. A negative stress is compressive. For now, this is not true in the upcoming version. There is a steady state solver, but for now, when you're doing a fluid solve, it's always transient. Okay. You're always doing a transient solution. Now, if all you care about is a steady state solution, again in the current version, if all you care about is a steady state solution, then you can play games with the fluid modulus to converge on the steady state solution faster, right? Because a steady state solution is independent of the fluid modulus. So you might as well use whatever you want that gives you the best numeric characteristics. And that's a trick. We'll show you how to do that. Okay? How to pick the right fluid modulus. FLAC2D models the flow of groundwater through a soil or a rock or whatever a permeable solid and the effect of that water on the solid. But which part of that is important is kind of up to you. Sometimes you just want the one-way coupling. You just want to know what the effect of that water pressure has on the material response, the likelihood that it fails in shear. Okay. Sometimes you need full two-way mechanical coupling. You actually need to model the development of pore pressure in response to mechanical changes. And if you get to pick which one is important, and also it's important to be aware of the relative timescales of these interactions, right? The mechanical response versus the fluid response, because that affects how you set up the model. If one's happening much faster than the other, as is pretty common, there's no reason to do a fully coupled analysis. You can separate those things in time and do them separately, and it's much more numerically efficient, okay? Code handles both fully saturated and phreatic surface flow, unsaturated flow. Pore pressures are always 0 above the phreatic surface, this version of the code. We do the full saturation suction stuff in the new version, but right now it's just a cutoff model. I'll show you later. There is an adjustment to the permeability made when a node is partially saturated, or a zone. The average saturation of a zone, I should say, is partially saturated. Basically, we use a cubic law, and I'll show a graph of that later. We do not do capillary pressures. That's not supported anywhere in the code. We don't do two-phase flow. For those of you who are in the petroleum industry and might be interested in that, that's not supported in FLAC2D yet, or in the new version, actually. Yet. A very common thing is to do a consolidation analysis. So where changes in pore pressure change effective stress, which affect the response to the model. Generally, some zones fail if it's at all interesting. Some zones are going to fail and adjust the stress state. But then when those zones fail and adjust the stress state, they might compress zones and cause volumetric changes, which are in turn going to cause changes in pore pressures, which are going to readjust.